Welcome to Spirit of Might, my channel devoted to curiosity in mathematics. In this video, we will show a link between pi square and the Fibonacci sequence. Pi and the Fibonacci sequence are probably the most famous objects in mathematical literature. And in this video I will introduce the Fibonacci sequence, and I will give you the proof of Binet's formula, which gives an explicit expression of this sequence. We will give a power series expansion of arcsin x squared. We will compute sine pi over 10 and sine 3 pi over 10, and finally we give our formula which gives a length between pi square and the Fibonacci sequence. If you stick around until the end, you will know how to prove Binet's formula, how to give the power expression of arcsin square, how to compute sine pi over 10 and sine 3 pi over 10, and finally how to get this mysterious formula. So let's go. In 1102, an Italian mathematician named Leonardo de Pise and known as Fibonacci introduced a sequence which became famous later. This sequence is called the Fibonacci sequence and has to do with rabbit reproduction. This sequence starts by 0 and 1, and then any term is given by adding the two previous one. So it's began by 0, 1, 1, 2, 3, 5, 8, 13, and so on. This sequence has been studied extensively by mathematicians, and even there is a journal devoted to this sequence named the Fibonacci Quarterly. In 1843, Marie Binet, a French mathematician, gave an explicit formula of Fn, which involved the golden ratio alpha equal 1 plus the root square of 5 over 2. So let's start by proving Binet's formula. The idea behind Binet's formula is the following. It's this relation. If you take x, a solution of this polynomial equation, then x power n equal fn x plus fn minus 1 for n from 2 to infinity. And Fn is of course the Fibonacci sequence. Of course we will prove this. The proof is easy and it's done by induction. So for n equal 2, we have x squared equal f2x plus f1, because f2 is equal to 1 and f1 is equal to 1. If we suppose that x power n equal fnx plus fn minus 1, we get that x power n plus 1 is x by x power n, but x power n is this expression. Now we get here, we factor by fn, we get fn. Fn x square is fn x plus 1, and we factor by x. x is equal factor fn plus fn minus 1, but fn plus fn minus 1 is just fn plus 1x plus fn, and we have done. So we get this property. If you take a solution of this equation, then x power n is equal fnx plus fn. So now let's solve this equation. The solution of this equation are actually the golden ratio and beta 1 minus the root square of 5 over 2. So we have that alpha and beta satisfy the previous relation. So we get that alpha power n equal to alpha plus fn minus 1 plus and beta power n equal. And we subtract these two expressions to cancel fn minus 1, and we get that alpha power n minus beta power n is equal to alpha minus beta fn equal alpha minus beta is the root square of 5, and we get and now we get that fn, we get the Binet's formula. If the power expansion of arcsin x square. So let's start by recalling the definition of arcsin. We know that the function sine is strictly increasing in minus pi over 2, and it's continuous. So it's bijective and has an inverse, which is arcsin. Arcsin is the inverse of sine on the interval minus pi over 2. So we have for any x in minus 1, 1, sine the arcsin x is equal to x, and only for x in minus pi over 2, we have arcsin sine x is equal to x. Moreover, arcsin is derivable on the open interval minus 1, 1, and its derivative is 1 over square 1 minus x square. Okay, so now let's give the power series expansion of arcsin x square. Arcsin, so we will prove this formula. And what we will do, we will show that arcsin x square satisfies a differential equation, and we use this differential equation to find relations between the coefficient of the power series expansion of arcsin x, and we will get the desired formula. So let's start. Put y equal arcsin x square. Its derivative is equal to arcsin x 1 over square 1 minus x square. And if you take the power, the square of the derivative, you get this formula. Now we multiply by 1 minus x square, and we get this formula. Now if we derive this formula, we get the derivative time this function, and this time the derivative, and so on, and we will get this relation. Now minus x square of the derivative, we can simplify by the derivative of y, and we get that y satisfy this differential equation. Now we will take the power the power series expansion of Arcsin and use this relation to find a relation between the coefficients of the power series expansion. It's a classical method and it's very used to resolve differential equations. So let's go. So we have this differential equation. We write down y as a power series expansion. We write its derivative and y derivative to the order 2, and we get, now we use this relation. Now if we multiply, we take the xn coefficient here, so we get the coefficient of the second derivative and this one minus x square the second derivative, so we take this one minus, and we identify by x the derivative of y, and with this formula, so we get now this relation between the coefficient of the power series expansion of y. Now the problem is we are left with this problem to determine which is the sequence an satisfying this relation with the condition a2 equal to 1 and a0 equal to 0 and I1 equal to 0. So if we factor, we get this relation here. Okay, so we have now, we are left with this problem to find the sequence which satisfy this relation. We must, here we have an plus 2 in function and an, but since a1 is equal to 0, we will get a3 equal to 0 and a5 equal to 0 and so on. So we will get that a2p plus 1 is equal to 0 for any p. So now let's see what happened for the even rank. a2n plus 1 equal to this relation with. Now we will use this relation to show that our sequence is actually the sequence we are looking for, which given in the formula of the power series expansion of the power series expansion of arcsin x square. So we will show by induction, by using this relation, and by induction we will show that a2n is equal to power 2n minus 1 over the binomial coefficient n to n multiply n square. So it's straightforward induction. For n equal to 1 we have this relation is satisfied. We suppose that we have this relation and we compute a2n plus 1. So we use this formula we get here, and we will replace a2n by this formula, and we will write thing in a right way to get the desired formula. So we simplify and we will get what we want. The power series expansion of arcsin x square. Now we will compute sine pi over 10 and sine 3 pi over 10. And okay, so we start by recalling the binomial formula, Newton binomial formula of a plus b power 5, so we get is equal a5 plus b5, 5a4b eb4 plus 10 e3 b square plus a2b3. And we will use the Euler formula. We have ai p over 10 power 5 by Euler formula is ai pi over 2, which is equal to cosine pi over 10 plus I sine pi over 10 power 3. So we have this relation. So this means that the real part of this quantity is equal to 0. We have a similar formula for ai 3 pi over 10 power 5. We get this formula, and also here we will get that the real part of this quantity is equal to 0. Now we put a equal cos pi 10 and b sine pi over 10. And we compute the real part of a plus ib power 5. We get this formula, and it is equal to 0. Now we replace, so this relation, we will use that the sine square is equal 1 minus the cosine square, or the cosine square equal 1 minus the sine square, and we replace, and we get that sine pi over 10 and sine 3 pi over 10 are actually the positive solution of this equation, because we replace here a by this relation, and we get that b square satisfy this relation. So now we need to compute sine pi over 10 and sine 3 pi over 10. We need to solve this equation and to find the positive solution of this equation, because we know that this quantity are positive. So we solve first. We put little x equal capital X square, and we get that x square is equal 3 plus square root of 5 over 8 by using the classical method to solve equation of degree 2, and we write this this quantity as a square. You can check that indeed the square of this quantity is equal to this one, and we do the same by the other solution, and finally we find that the positive solution of this equation are indeed 1 plus the root square of 5 over 4 and the root square of 5 minus 1 over 4. And we have the positive solution. So since sine pi over 10 is less than sine 3 pi over 10, we get that sine pi is this quantity, and sine, and we get the what we are looking for. Now we can move on and prove the last the last formula, namely the formula linking pi square and the Fibonacci sequence. The power series expansion of arcsin x square is given by this formula. We have computed sine pi over 10 and sine 3 pi over 10. So if we replace x in this formula by root square of 5 plus 1 over 4, we get arcsin of x is equal 3 pi 10, so we'll get 3 pi 10 square equal this formula with x equal to this quantity. And we do the same for sine pi over 10. So we get these two formula. And as we can see, we have the expression of the ratio, the golden ratio, which appear in Binet's formula. So if we take the difference between these two quantities, we will get here f to k in this relation. So we get this formula, and now we can multiply by 10 over 8 to get what we are looking for, and we have down, and we get this beautiful formula which gives length between pi square and the Fibonacci sequence. So to support the channel, please like, subscribe and share, and thank you.